Okay, so we go now to source operation and zero. So the first thing talks about the laser effect, and that's there is one value. Oops. So the laser actually is one of the things that the names mean something. It's light amplification by stimulated emission of radiation. And it's important because there is coherent light. So every photons that are emitted, they actually are pretty much the same frequency, that also interface with each other. What does it mean? If you take, like, even if you go on matter, you sum up a number of sinusoids, okay? And on the first type, you just sum it up with having them having a random phase, and then on the second instance, you sum them up having all the same phase. What you come up is that here you get something like that. While if they are coherent, we basically get much bigger. And the point that it's very easy. I mean, the point is that the highest part here sums up with the highest part here, and sum up with that. So basically, you have the sum of all of them in one. But if they are random, this part here basically subtract from this. So basically, they neutralize each other. So basically, it's like this two never existed, and then this one is marked at second stage. So basically, you have something. You have some high peaks, but generally the high peak can be just like that one. It's actually much lower. So this will happen with coherent light, so this will happen in the bullet. The second part will happen with coherent light. Now, this difference is actually quite large. So imagine, so if you have non-coherent light, okay, so this is typical halogen light that you might have in a bad garden, and the 1 kilowatt, I think. I mean, it's quite a strong light, but it's for this stuff like for domestic use. Right? And I mean, you might get hot if you put your hand on top of it, because it produces heat as well. But just by comparison, at 1 kilowatt laser source is used to basically cut through about an inch of solid steel. So that's 1 kilowatt. So that's the difference we got between the two of them. Okay, one reason is because it's coherent light, so it's actually focused on one point. And the other reason is because, of course, it's more collimated. So the whole power is actually considered in a very small quantity. So how does the laser work? So the basic idea is that of absorption and emission of lights or radiation. So this is an example. These are hydrogen atoms, which has a proton and an electron. So everything, the interaction between energy and matter is pretty much reduced unless you go to nuclear explosion. But otherwise, with all the electromagnetic phenomena that we observe, it's mostly due to the fact that there is a photon. If the photon passes by there, it gets absorbed, but energy cannot be destroyed, so it must be stored somewhere. So basically, by exciting the atom, so by putting the electron in a higher energy state, it basically absorbs the light. And this is a kind of what we say quantized kind of things. So if the photon is not exactly this jump, okay, so this guy can only jump at definite high definite states. That photon has different energy, which doesn't correspond to any of those. Then it just passes through and is not absorbed. And even absorption is kind of a statistical thing. But anyway, imagine now that photon has exactly the exact energy to allow it to power up. So I could go to the next state, it's absorbed, and since naturally the electron tends to be the lowest energy state possible, after some time it will decay again and it will be absorbed again. That's simple. Another example is that I have a photon with higher energy. There you go up, and you can go up to the level. Again, that has to be exactly the same energy, that energy of that, otherwise it won't happen. So that's what absorption and emission of radiation is for atom, which is pretty easy enough. Another thing that can happen is that I can have a double absorption again. So basically what happened here is that this is absorbed, like that. Now, one option is that it is absorbed. Okay, it can actually be absorbed into the loop. Like that. Yeah. So it can be emitted in 2 times. It doesn't have to be 2%. It doesn't have to be emitted in once. Okay? It can produce basically 2 photons. One relative to the first step, and the one relative to the second step. And these are all probabilistic things, how they which one will happen. Now, the other thing that's very interesting now is what's called the stimulated emission of radiation. And that's a very interesting phenomenon, and you wouldn't imagine that for a while. But that's the basic of all, lasers and amplification, optical amplification. So it's very important phenomenon. So there is a here atom which is already been excited. somehow. So your electron is up there. Now, if a photon passes there, passes by the atom, and has the right frequency, so you can allow basically the atom to go back. So this photon basically has the same energy as this one storing. That's an important part. So what happens is that the photon goes there, and basically you induce it to produce another photon, which is exactly the same as the first one. So basically it has the same frequency and has the same phase. Okay. So basically this is just produce another photon which is in phase with itself. And that's a really important one. What I do. So another idea is that again, so I have, okay, yeah. So if you don't have the exact, so if the photon that comes in hasn't got the same jump energy for the big jump, like this one, but you might have less energy, it can still be possible to produce a smaller. So yes, the first step where he produces actually a photon which is exactly the same as the first one. Okay? And that's provided that the first step has the same energy as the yellow photon. But then the last step basically was a random generation. Okay? Okay, so this one is in phase, but the second one, the red one, will be just random emission. Okay? So these are very important phenomena for amplification and light. And we'll see now how they actually happen. So the laser was labeled. So the laser, you can imagine, is a bunch of protons, or protons and electrons. Okay? Now, a laser can be made with semiconductors and made with gases. But just to explain the basic principle, you have a certain number of atoms, like that, and then you have two mirrors at the side. One mirror is totally reflective, and another mirror is, doesn't reflect all the light, but reflects most of it. So what happens is that, so if I want these photons to emit anything, first thing they have to be excited, okay? Because only when they're excited, they can actually get down to the normal level and emit sound. So basically, the first step is that I put a current, it's called a current one, that basically excites all these electrons like that. Second step is that there will be some photons which are randomly generated, so the natural decay will start as soon as they get excited. So that's the yellow photons. But as you see, the yellow photon is coming through the cavity, and it will basically, for the first effect to explain, we will generate other photons with the same phase and frequency. So that's, for example, the yellow one, and randomly another. What color is that?
It's the light. Purple.
Yeah. So dark like that will be created, and maybe a red one as well. And whatever energy is left, because those three are different energy. So whatever the energy is left on the atoms, it can either decay or it can be pumped up again. And we can be pumped up again. So now what happens is that they scout, so when you think about photons, the photons are both, people can imagine both as particles or as waves. Okay? But they definitely work as waves, okay? So they have a phase and they have an amplitude and a phase. So what happens is that these photons now, some of them will be reflected and some will not be reflected. Now because of the wave part of the photons, what happens is that whose frequency match exactly the frequency of the cavity are the one which will be most long-lived. So in that case, most of the photons will go out, but the red ones, which actually basically is a resonance phenomenon. Okay? So when the wave is equal to the size of the cavity, then you have that phenomenon which is called resonance. And basically that enhances anything that happens. This times basically means a lot of photons will get lost, but those that match the cavity will basically remain inside more time. What happens then? Now we have two red and one yellow. Now the red will go, so we pump again, so the pump is actually continuous. So the red will go will produce more, the other red will go will produce more, and then the yellow basically start. Okay. So the idea is that this resonance makes sure that the red photons remain in the cavity more time than the others. By remaining more time than the others, they basically are going to, the phenomenon, the simultaneous emission means that each photon that passes around can actually grab an additional photon. Okay? So if I have more red, they exponentially will grab more and more photons, and they will remain more time in the cavity. So that basically at the end of the star, the yellow one will totally, the other colors will totally die away. Okay? And that's what's called survival of the fittest. So the photon that fits most in the cavity is the one that starts creating a bigger population, and by creating a population is going to starve all the other photons, because they're going to consume all their photons. So they're going to get energy. So basically that will happen. So then it goes down the mirror, and then it gets affected, it goes, gets multiplied, and then a tiny percent of the light, as little as 10%, will actually leaves the cavity. That part that leaves the cavity is actually the light that is useful for you. Okay? All the rest stays in the cavity to keep producing this effect. So that's pretty much the way the laser works. So the important thing is basically that you have a resonant cavity, and that we can produce light. So the phenomenon produces light screwing into each other. Okay? Every time this goes up and down, they stimulate photon which is exactly the same phase. Okay? So that's why it is coherent light, okay? Because they're always close to each other. Now, is there any question at this point? So, when we go to actually see what happens really in the laser, so the point is that imagine this is a laser, so the resonant frequencies, actually there is a number of resonant frequencies, okay? Because by definition, it's not just one frequency which is resonant, but it's that frequencies and all the multiple of that, okay? So if I have, this is sine, mine is a sinus of x, and if I have sinus of 2x, that will also fit very well here, okay? So that we basically means that we have here, in that case we will have two wavelengths within the cavity. So the point is that usually there is more than one resonant frequency. And so we have some resonant frequencies, they are many of the gain, what the material used. Okay? So the material that you use are certain bunker, what's called the bunker. And basically that means that it has, so let's go back, two slides back on the, so this, the band gap, when you actually have real material, there's also atoms on top of each other, so all the energies are not just still quantized, but there's way more than that. But there's still a preferred frequency, which kind of, you can imagine that this preferred frequency is associated with the preferred step of the photon. Okay? So there is one frequency which works better than the other. Okay. So, and this basically, this is associated with the gain of the medium. Okay, so here where the frequency matches as well what's called the backup, the energy backup, you have the peak, and then you start sliding down. The truth is that this actually is kind of more flat than it looks here. Okay? So this is the loss of the medium. Okay? So basically it means if I'm not exciting the medium, the light will just be absorbed itself by the laser, so there's nothing to be produced. But once I excite the laser, then I get this kind of gain. And basically when the gain is equal to the losses, then it means that my light is not absorbed anymore in the laser. I can actually have this called lasing phenomenon. Now, since we have resonant frequencies and we have a certain amount of gain, what actually happens is that you will have more than one line. Okay? So if I use a normal laser, the DFB laser is a fabric laser, which is this kind of laser, with 2 meters we have lasing a mirror. What I have is not just one frequency, okay? One wavelength. But basically the signal spreads off a certain number of carriers, let's call it. Okay? Now these can have a line with about 400 to 500 gigahertz, which is that a lot of those are not. Well, you can think if I want to do a multiple wavelength system, I normally space one each 50 gigahertz. Okay? So basically I cannot use this for a multiple wavelength system because of the growth. So it works fine for single wavelength, but I can't do things wavelength multiplexing. I could do coarse multiplexing, or basically, instead of putting 80 wavelengths, I only put about 8, and then it will still fit. So, but that's what happened with the time. So then, how do I build? I mean, it's a bit of a waste that I have such. I mean, because this one are actually quite narrow in a laser. It's only the fact that I have more of them, and they're totally useless. I mean, there's no reason to have those ones, so they don't make me anywhere. So then, can I build a laser which actually has only one? Because once you get one, then you may get everything around. The reason is that there are some lasers called single mode lasers. So basically, there are two ways that work. So it's all based on something which is called the corrugation of the laser. So this has the same mean that it's all about what's the wavelength of the photons and all. It's kind of a resonant frequency. A resonant cavity. But it's a distributed cavity. So basically, the photons travel and they get reflected at each. Some of them, a little bit of them, get reflected at each point. Okay? And they basically, when they get reflected, they go back. But now I can tune among all those wavelengths that I have. I can actually, I have another degree of freedom, so I can actually choose this to be exactly the one I want. So instead of having 5 or 7 line width, basically I can actually tune this one to be resonant just with one of them. And basically when that happens, basically it's all the photons affected, they all end up at the same phase here. Okay? But at this point, only the photons with that particular frequency will be. Okay? Basically, I have two resonant frequencies. Here I have two types of resonance. One is the big resonance, okay, that goes up and down like that. And that will be resonant for like a certain number of wavelengths. But within those number of wavelengths, I can have another resonance, which is this one. And this will actually further select only one of them. So this one, the first one is called DFP. Basically, this happens on the laser. The other one is called the other detector. Basically, I still have this separate. So this is my normal laser. And the light that goes out, it gets filtered like this. It's two-way filter. But with those, I can actually have a line width of 100 megahertz, which is quite good for a fiber system. So basically means all the band I occupy is not due to laser, it's just due to modulation on top of it. Tunable laser. So the laser we talk about are based on resonance. Okay, so resonance is a spatial thing. So if I have a certain space, then the wavelength will move forward and back at that particular frequency. So it's a kind of fixed. So how can I have a tunable laser? A tunable laser basically means a laser where actually I can twinkle to change the wavelength or the frequency. So it's basically, I am intuitively, if I have a laser with if I have a laser with a resonant cavity, which is this size, basically if I can do anything to move this in either direction, I will actually have this bigger like that. Of course, now that this is the same medium, so the resonant frequency now will be a different one. As soon as I change the resonant frequency, then automatically the laser will go and create a different wavelength. Of course, within the possibilities, right? Because there are still the preferred frequency at which the gain is maximum. So one idea is actually, I think the word laser, which basically were built so that I could actually twinkle and I would actually increase the size of the cavity. But they are not, I understand that's not very practical. And that's why you cannot do that directly. And I mean, tunable laser now can switch in the order of nanoseconds. You'll never be able to twinkle in the nanoseconds. So that's what's back. Another thing as well is that, so the resonant frequency is the length, you can say the length L, okay? But actually, what the laser sees is not the physical length, it's what's called the electrical length, okay? Which is due both to the length and to the refractive index length. Okay? Because as I was saying before, so there is a relation between this, the frequency of a laser and the wavelength. Okay? So for example, this depends on the refractive index. For example, the refractive index again reflects the speed of the light. So if I have N1, this is a specific material here. So basically the speed will move at a certain, the light will move at a certain speed, could be this one. So if I have a certain frequency, which is like this, and I move at a certain speed, I get this way. Now if I change N1 to N2, and so that now light will move faster, for example, If I have the same frequency, but I move faster, then we see they are different already. Okay? So you can understand that by keeping the same area, but by changing n, I can actually decide which wavelength will fit here. So the idea of the tonal delay is basically not to change that, but to change something inside. And then, so the refractivities can change in different ways. So one thing is temperature. So all these values change with temperature. So I can actually change the temperature of the laser so that I will different n. And whereas I think I can do it by changing electrically the laser. So by changing the electrical properties, I can vary this by over n. So there is that I can tune the laser, and I don't have to move the card physically, but I can do it by changing the n value. Okay. So why are those useful? Now, tunable laser, well, the type application where I want to be really dynamic. Okay, so I want where one at the beginning. It's a bit like dynamic spectrum. Okay, so with the radius, you can actually change the oscillator frequency very easily. So one reason is that one, I want to use the network more dynamically. That's not the main reason why it's not at the moment. One reason, not only the main reason are like storage reasons. So one size fits all. So imagine I have a WDM system, multiple wavelength, right, with 40 lasers. If each of those lasers work at a specific frequency, and one of them breaks, basically I have to call the provider and say, okay, I need another one. And they tell me, okay, I'll give you one in a week. But if you are serving some customer which cannot wait for a week for the laser, what you have to do is that you have to stock in advance. If I have 40 wavelengths and I want to stock them in advance, then I have to need to buy another 40 wavelengths because any of those would fail. Okay. So I need a stock of 40 different ones. And maybe I need a stock of twice the time because if something fails twice, for some particular reason, then I want another one. Well, if I use tunable lasers, then if I buy two lasers, those will cover for any failure of wavelengths. So this is one of the reasons. And the same thing, this is true both for the manufacturers. So the Cadillac manufacturer will have to stock, a much larger number and go through the sales provider. So this is probably the main reason why tunable lasers are used at the moment. The second one, of course, is the compatibility. So if I build a network is much more dynamic, then I need things to be tunable. And that's what's used most for research purposes. So, okay, I said already. So the idea is to change the resonance tracking mechanically, not only physically, but it's hard to do. But electronically, by changing the tracking. So now let's go to signal modulation. So at the moment I have a laser which is a source of light. Now if I want to put modulation variables, I have to produce something that can change the properties of the light. Now, an example of light modulation that was used for, I think so many uses or military use. So you have a constant source of light, and then by switching on and off, so you don't switch on and off the light, that should cover it on and off, you produce a bunch of 1 and 0. Whereas, this is used with the Morse code, so I can do a point or a line, depending on how long you keep it on. And there's another type of modulation as well. And smoke signal are actually kind of light modulations. Because if you think about it, basically, the light, without the smoke, the light will come straight to me, but because of the more smoke, the light gets reflected. So basically, by doing smoke signal, I actually do modulate light. I change some property. Okay? And information can only be transmitted by changing something of the card. There's no information that can be carried on a sinusoid, for example, if you don't change any property. So, what kind of modulation do we use? So if you know anything about wireless modulation, then your lab will be very disappointed. Because pretty much up to at least 5 years ago, the only modulation used in commercial system was on. Basically, bit 1 was light, bit 0 was no light. Light, no light, light, no. This is still used in most systems, but now they kind of change it because of some advances. So one is one of modulation, one is amplitude modulation, and this is a particular case of this. Let's say amplitude modulation basically I have 1, I send a certain power, then I decrease the power 0 now. I can use frequency modulation. I still match the wireless. I can associate one frequency with the one and another frequency with 0. And I mean, so what you use in wireless, what you use in optical, really depends on what is technologically feasible. Okay? And even in optical, even in wireless, you can only start doing like phase modulation, for example, when you start doing coherent detection. Okay? So if you cannot do coherent detection, then you're pretty much limited to amplitude modulation and this frequency modulation. But for the optical, because it's such high frequencies that you are only 1 gigabit or 10 gigabit, it was very hard. It's always been very hard to catch up with the phase movement. The phase, those frequencies, working like that, was about 10 terahertz. And you work about 3 terahertz by frequencies. Okay, so it's nanometers per, so micrometers. So they move very fast. It's always been very hard to catch up with them. But I mean, lately people have started using also phase modulations. Okay? And that's because just in the past few years they have managed to do coherent detection of a signal. So they also managed to get phase. But again, so laser modulation, again, up to a few years ago was basically a bunch of 1 and 0, then switch on the laser on and off, on and off. Ideally, you do it with a square pulse. Okay? But by definition, if you have a square pulse, first of all, it's not feasible, and if it was feasible, that would occupy a bandwidth that basically will be infinite, because you have a transition. And if you were able to do a transition like this, then there's no point of keeping all this time the same signal. Okay? If you're able to do something like this, then you basically will go down straight away, and then you have a much higher delay. But the point is that this is impossible. So what happened in theory is that you have 0, then you have the laser that starts building up to a certain point, and then you switch it off, and we take some time to get down. So what you send are what kind of gas and shaped pulse. That's one thing. So as modulation type, so imagine that at the top is the digital data you want to transmit, so that's still in your computer. And when you start signing, so one modulation train is called the return to 0. So you go up, and then you have a 0, you go down. But then if you have 2, 1, every time you go back to 0, then you go up again. That's nice modulation, but it occupies kind of a larger bandwidth than the second one, which is no return to 0. No return to 0 basically means either 1, I go 1, I go 0, go 0, but if I have 2 1s, then I keep going. I don't stop. And you can see that, this one has more transaction. Okay? So every time you move a signal, you basically it increases bandwidth. So the more I filter up and down the signal, the more the bandwidth will increase. But if I have more constant type of signal, the bandwidth tends to be more complex. So in fact, any Z complex, the bandwidth and more Z is more used. And there is other types, phase modulation, DPSK, that's pretty much another wireless. And then there's multi-level modulation also used. So I go to modulate my signal now. So how do I modulate the signal? Well, there are two methods. One is called direct modulation. So pretty much you feed the electrical signal on top of the laser, and the laser will basically create the light on and off. The way this actually goes is basically the way you do. You have a laser. So if you want to produce a current with a laser, you want to produce a light with a laser. You apply a current. At the beginning, there's no light. You start going up, and you see no light, and then there is a point where the figure that I showed before. So the gain of the medium you're producing is equal to the loss. From that point on, you actually start having the laser. Now, what happens is that if I put my signal, so if I put a constant signal which is just below the laser point, and then I apply an electrical signal which is like this on top, then basically as soon as the one comes in, the laser is basically at the edge of the laser. So as soon as the one comes in, the laser will start gazing, and then it goes down again. So this can be done, and it's the cheapest way because you basically don't need anything. You just directly apply a moving current to the laser. It's inexpensive, and it can be done reasonably fast because the laser is very fast. The only problem is that the refractive index depends on the current. Okay, And since now the current is not flat, so the current I'm actually supplying current which varies, what happens is that the signal gets a phenomenon which is called chirping. So basically it means that the frequency is not the same throughout here. So we start with a higher frequency and then it kind of slow down. So it's higher frequency and then it goes up, and it's lower frequency and then it goes down. And that's that. I mean, it can be sometimes used as an advantage, but the idea is that sometimes it is a disadvantage. The other thing is doing external modulation. So now the laser just create a continuous light. And what I do with a modulator, which basically is kind of it's a kind of a shutter on top. It can be done in different ways, but the idea is that here is the light, and you do this something is up and down and down. So you see light when it's a 1, you don't see light when it's a 0. The way they actually do it, they use something which is called interferometers, which basically quite quickly can change the light between being in phase and being out of phase at the output. So by applying a certain current, I can have the light to be totally out of phase. So basically at the output there's no current generated, so it all goes back. When they are in phase, it basically goes through straight away. So with this thing, I don't have to chip just because the laser is actually producing a continuous light. It's only to think about the change. Now, the things there, the transmitter, of course, we need to have receivers. So receiver are the other side, on the other side of the chain. So I transmit light at a certain point, I have to get it back into digital signal. And the reason is simple is because anything we do is digital. There's no analog thing to do anymore. Could be a switcher, could be a router, could be a computer. So I have fiber, I have light, the light goes in, the receiver basically gives me back the corresponding electric signal. So how does a receiver work? The idea is pretty much the same as having the absorption and so producing light and absorbing light within an atom. What happens is that I have a photon that goes there. So this for example shows a semiconductor. Semiconductor is divided between 2 points. So one is the valence point and one is the conduction point. So in a semiconductor, this is kind of finite. Right? So if I have a conductor, for example, this one will be overlapped. Okay? That basically means in a conductive element, any time I apply a current, the current will go through. If I have an insulator, like current doesn't go through, this one are quite separate to each other, which basically means I can't put enough current to have the thing electron go around, because otherwise we destroy the other. But semiconductor basically has this, which is basically just a valve. So basically by applying more current, for example, or by heating up the element, I can actually allow things to go up. So what happens is that in a semiconductor, by exciting this, I can have some electron come up. Once they're out, they are free to move. Now what happens with the photon is that this photon will be here. So that photon is actually the element which triggered an electron to go from here to here. The photon goes there and is absorbed like that. So once that's absorbed, I only need to apply a small current so that it can move up and down. So I apply the current, and this will move, basically move. Right? So the current I apply remains there all the time. Okay? Imagine now this current. So there is a positive, a plus here and a minus here. So basically, anytime anything gets excited, I get a current control. So this basically allows me, if I detect, I start detecting the current, I realize that each photon that comes in produces one, let's call it 1 unit of current. Okay? So I have a bunch of photons. They hit here, they are absorbed, and the other side I get you basically get an electric pulse. Okay? So I have an optical pulse here. This is an optical pulse that is absorbed. It creates a number of electrons, which will go through, and then we detect that as a current. That current which are pretty much in shape of optical pulse. Yeah, so the only thing I have to be careful, of course, is that the energy of the photon that comes in has to be at least to be higher than the energy of the background. Right? If the photon has not enough energy, then the electron cannot jump out. If it doesn't jump out, it's not going to run. So that's the constraint. So same sensitivity. So different materials have different band gap. So basically there is a cutoff, let's say there is a cutoff kind of frequency. And if I don't reach that one, then it's physically impossible for me to do that. So some of that power will be absorbed, and that will be a current called IP. And the responsivity of the receiver is defined as how much current is generated in amperes for each watt of incident light. The practical values are around 1 or 2. So that's basically it. So the laser transmits my signal, I modulate it, and then the receiver gives me back to electrical. And that's the way it usually happens. So there's other type of photodiodes, for example, some are called avalanche photodiodes. So this works on the fact that if, when I said I put a current here, okay, I put a current here so that any electron generated will be accelerated and I can detect it at the end. The avalanche is used on the fact if I increase this a lot, okay, if I increase this, this voltage here much more, then this electron will go there, but it will go there really fast. Okay? As it goes fast, it basically excites back the electrons. Okay? So as it moves, this basically brings more electrons away. And this basically means that for each photon, I have many more electrons generated. And that means that it's easier. I get a bigger signal at the end. Okay? I can do more of a fat signal. The problem with that is that you will have a much wider sigma values. Okay? So imagine a pulse is a Gaussian, but by that thing, basically, the only initial photon is the real one. All others are generated, but as they are generated, they get they get a larger distribution. So that's the only problem. Good. So again, I was saying, so modulation has been the main modulation for a long time. But now people have started building for the last few years coherent systems. Coherent system works very well, more expensive, but it works very well. First of all, I can start using modulation like PSK and QPSK, which work quite well because they don't have any. First of all, they are not affected by amplitude modulation, so any effect that they have in amplitude when two signals interfere with each other. Because the amplitude, I can't delete that completely. And they work quite good, and plus they also have kind of higher spectral efficiency. Okay? So which up to now wasn't really a problem because the fiber had a huge amount. But now it starts getting a problem. It's getting a problem because basically the fiber there are some systems which actually manage to fill in the whole bandwidth available in the fiber. The whole bandwidth commercial. So by using higher spectral efficiency, I can send more data at the same time. The other good of this is that, so while the normal 1-0 signal, they only use what's called directly detected signal. So anytime I transmit the signal, I have an amplitude in the phase. The normal systems, they only detect the amplitude. So they lose all the information about the phase. But with this one, I also keep the information about the phase. That means that, for example, if my medium goes through a certain dispersion, I could actually, if I detect all the information of the signal, then I can apply digitally the inverse of the transmission channel. Okay? So I can actually reverse the dispersion afterwards. I can only do that because I keep the whole information of the signal. Okay? If I only look at intensity, once two signals are overlapped, I cannot distinguish them anymore. So basically, what happens is that they get mixed up once they overlap. And there's nothing I can do to reconstruct what happened before. But now I have also the phase, which basically means these two signals are still distinct to me because they are still distinct, even if they overlap in amplitude, they are still distinct in the phase. So the idea is that now, with this system, I can actually manage to contract dispersion digitally at the end.